Okay, so in the last video, we had a look at gradient functions and derivative functions, and what these look like graphically in comparison to our original function. So we're going to explore that a little bit further this video, and the reason being is it's going to help us determine the derivatives of sine of x and the cosine of x. So if we start off with this red curve here, this function of x, our red curve, is actually equal to the sine of x. Okay, and what we're going to do in blue on this empty axis down here is we're going to plot the derivative function. So we're going to see what the derivative of sine of x is. So we're going to plot its function and see if we recognize that curve. So if we start off remembering that anything above the x-axis on our derivative curve represents a positive gradient from our red curve, and anything below the x-axis on our derivative curve, or our derivative graph, represents a negative gradient on the red curve. And all of our critical points of this red curve, and I'm going to dot all of these in here, are all going to have a gradient of 0, right? So they're all going to be x-axis intercepts. So likewise here, we marry this one up here, and this critical point, they're all going to sit on our x-axis like so. So that's the starting point. And what we need to do now is we need to basically fill in the gaps in between all of these critical points. We need to link these critical points up. So what do we see is happening from our first critical point on our red curve to our second critical point? And on our blue curve, that's this region here, right? So what's going on in between there? So we see on the red curve, we have a positive gradient all the way from the first critical point to the second critical point. Okay, so it's all going to exist from here to here. Our curve is all going to be in this region here. Okay, we just need to work out a rough shape. Well, we can see that the gradient changes here, okay, at that point. So it's still positive the whole way along, but it starts becoming less positive. So here, it's super steep. Here, it's still positive, but it's less steep. So this, we worked out in the last video, is going to represent a turning point. Okay? So it's going to turn at this point here. So we're going to be able to match this up to look something like that. And if we do this for all the spaces along, so we do the next one, from our second critical point to our third critical point, we have a negative gradient the whole way down. Right, so it's negative, 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 the whole way down, all the way to the third critical point. And it starts becoming less negative per se, or less steep at pi. Okay, so at that point, we're going to have a turning point. And we worked out it's all negative gradient the whole way down, so it's all going to exist in this negative region down here. So it's going to come negative, 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 and it starts becoming less negative, or it hits its maximum negative gradient at this point, and starts becoming less negative up to 3 pi on 2. And then if we repeat the process from the third to the fourth, we have a similar situation, or the exact same situation as the first one from 1 to 2. So that's going to come like this, right? And of course, it's going to continue. In this case, we won't complete a full cycle, but we'll get down to there and it will start coming up the other side. Okay, so that's just repeating what we did from the first to the second to the third. It's going to be a repeat for the fourth to the fifth to the sixth sort of thing. But now, can we recognize this curve? Well, this curve, this derivative function of x, this actually represents the curve, the function of x. This is actually equal to the cosine of x, right? So this graph actually represents the graph of the cosine of x. So the derivative of the sine of x is the cosine of x. So I'm going to write that in black because that's going to be important, is equal to the cosine of x. Okay? Now, without going into too much more detail, okay, we've got a rough idea of where this comes from. The official, or the way to cover sort of all boundaries with this is to say that the derivative, I should put in the derivative here, sorry. The derivative of sine of x is cosine of x. The derivative of the sine of some function of x, so it could be 7x plus 4 or 6x squared or something. So the derivative of the sine of some function of x is equal to the derivative of that function times by the cosine of the original function. Okay, so don't worry if that's looking a bit too complicated at the moment. We'll do a quick example. So that second one in yellow there is the one that we need to remember. Okay, so for example, we are asked to find the derivative of sine of x cubed. Okay, well in this case, our function of x, is equal to x cubed, right, from our formula. So the derivative is going to be the derivative of the function of x, which is 3x squared, times by the cosine of the original function of x cubed. So the derivative of sine of x cubed is 3x squared times cosine of x cubed. Okay, so that's working out the derivative of the sine of x. Now, it's good to see what's going on there with the graphs, but the main thing to take away is this formula here. Okay, that's the one that we need to remember. Okay, so moving on down this page, we're going to do the same thing as we did, but this time, this function of x in red is actually equal to the cosine of x. And in blue, we're going to take the derivative function and see if we recognize that function. Okay, so here, let's look at the red at all the turning points, right? This is where the gradient is equal to 0. And remembering on our empty axes where we're going to draw the gradient function, these are going to represent x-intercepts, okay? Because we have a positive gradient up here and negative gradient down here. So when the gradient is 0, these are going to marry up on our x-axis. And we now just need to fill in the curve or fill in the gaps between these points. So if we look at this region here, this is all negative gradient, okay? It's all negative, it's all negative, it's all negative. And it gets its most negative at this point here, pi on 2, before it starts becoming less steep. So that's going to be a turning point. And it's going to turn down here because it's all in the negative region. So we have negative gradient, negative gradient, negative gradient up to there. And if we now come up the other side, this is all positive gradient, all up here. And it becomes its most positive at 3 pi on 2. So this is going to come up here, positive gradient, turn at 3 pi on 2, and start becoming less positive. We'll do the last region, which is down here, which is repeating what we did first. This is all negative gradient and turning at 5 pi on 2, so becoming its most positive at 5 pi on 2. And now if we, in green, I'll sort of draw the carry-ons from here sort of thing. It would come out like that, and that would come off the page there. Can we recognize this curve? Well, this curve is actually equal to negative sine of x. Okay, so if we come up here, we saw that the sine of x was that one in red. Okay, this one here is it sort of flipped upside down. It's the negative version. So the derivative, we can say that the derivative of cosine of x is equal to negative sine of x. So that's an interesting relationship there too. And to put it formally, to cover all cases, we can say that the derivative of cosine of some function of x, again, that could be, 4x squared or something, that is actually equal to minus the derivative of that function of x times by the sine of the original function of x. Okay, so in this case, this is the one that we want to remember. So we've got two major formulas that we want to remember there. And if we do a quick example, we can say that the derivative of cosine of 4x squared plus 7, okay, that is going to be equal to, well, in this case, our function of x is 4x squared plus 7. So the derivative of that function of x is going to be 8x plus 0, so 8x. So the derivative of cosine of 4x squared plus 7 is negative 8x times the sine of the original function, 4x squared plus 7. Okay, so there we have it. We have our derivatives of sine and cosine, okay, and we've looked at them sort of graphically, where it sort of comes from, that this is in fact the case, and we've come up with some really important equations. This one here is an important formula that we need to know, and this one here is an important formula that we need to know. okay? The final one that I want to touch on, and I'm not going to draw a graph or go into too much detail for this. This is just one that we need to know. And that is the derivative of e to the power of some function of x. Okay, now e is just a constant number. Okay, it's a magic number. It's sort of one of those ones like pi. Okay, it's sort of the, we got like the pi, which is represents or relates to circles. E relates to what we call our exponential functions. Okay, and they're the functions that look something like this. And our e is sort of like the pi of our exponential functions in a way. And it's just a number. E is equal to, I think it's 2.71 or something, okay? But the key takeaway is that it's just a number, okay? And the important thing to note here, without going into too much detail, is that the derivative of e to the power of f of x is just equal to the derivative of f of x times e to the power of f of x. So this here is an important formula to know. And for example, with this one, if we were asked to find the derivative of, let's say, e to the power of 7x, well, this is going to be equal to the derivative of this 7x, which is just 7, times e to the power of the original function, 7x, okay? So that's a little example for our e's. So not too much for this video. We're just looking at the derivatives of sine, cosine, and e to the power of some function of x, okay? And we looked at where those derivatives came from. And we just have to take this one for granted for now, okay? We just see this one as is. All right, thank you.